This segment we're going to talk about calculating thermodynamic properties for ideal gas mixtures. It's going to be a lot of equations, so just bear with me, but it's important to make sure that you're really comfortable with these units. So delta big U, it's equal to mass times delta little u. You know that, so this is just referring to the mixture. It's equal to delta big U for each individual component. So it's what we call an additive property. I can also put this in terms of m delta little u for each of the individual components. And you'll notice how the units still work out to kilojoules. Or I can also put this in terms of the number of moles, but if I multiply this by the number of moles, I need to make sure that that U bar, or that my internal energy, is in terms of on a per mole basis. So that's where that U bar comes in. And we have U bar values for 5 different types of gases that are commonly encountered in this class: carbon dioxide, carbon monoxide, water, nitrogen, and oxygen. And those are tabulated in A23 and A23E. I can calculate delta little u as well. So this is the sum of the mass fractions of each component times delta U for each individual component. Or I can use the mole fraction. You can see it gets a little bit uglier. I've got to divide through by the molar mass. But if you're paying attention, you can notice that how the units is a little bit more complicated, but it still works out to kilojoules per kilogram of the mixture. All right, so taking those last two equations right there, let's look at what we can do if we assume that specific heats are constant and how those two equations are going to change. So we would use the assumption that specific heats are constant if your delta T is not that big, if it's on the order of a couple of hundred degrees, or if we don't really have a choice. So if you have a gas where you do not have U bar values tabulated, such as you would find in A23 and A23E, or if you have a gas that you do not have U values for. So we have U values for air, but we don't really have it in your tables for any other gases. So it's not to say they don't exist, they're just not in your book. So if we don't have tables, then we kind of don't have a choice. So I'll be specific about if I want you to make the assumption specific heats are constant or not in this class. All right, so that first equation we could put with the mass fraction, you can put that delta little u in terms of CV delta T. You'll notice that I put a subscript I after each one of those terms to indicate that I'm talking about the component. But you can see on that last delta T, I just dropped it. And that's because by Dalton's model, the temperature of the component and the temperature of the mixture are equal to one another. So this works out still to kilojoules per kilogram of the mixture. All right. Let's look at the one in terms of mole fractions. So still looks kind of ugly, but we've got the delta U bar in terms of CV bar delta T. CV bar values are not tabulated in your book. CP bar values are, and that's in A21 and A21E. And you can kind of finagle what the CV bar value is going to be. Because CP and CV are related by the molar mass, or the CP and the CV values for a gas are related to by the specific gas constant. So you can kind of finagle that. It's something that I might ask you to do on a quiz where you have a lot of time to work through that. But in a testing environment, probably I'll just give it to you. But I do want you to know that you can go between CP and CV and CP bar and CV bar. You have the tools accessible to you to be able to do those things. We have similar relationships for enthalpy, so your H bar or your H values. Those are on your equation sheet. They look just like what we just saw. You're just replacing the U's with H's and the CV's with CP's. But they look exactly the same, so I don't want to go over them again and waste your time. Let's look at the entropy. So delta big S, this is equal to m delta little s. That's recognizable, you know that. And that's in kilojoules per Kelvin. So this is equal to the sum of the mass of each component times delta S for each component. And delta S for each component, you have an ideal gas. So delta S for an ideal gas is this guy right here. You got S02 minus S01 minus R natural log P2 over P1. But I do have a little subscript I after each one of those terms, so it's referring to the component. So S0 for the component, which is only a function of temperature, and you can look those up if you have it. And you have that for air, for example. You can look in your ideal air tables. That pressure is the component pressure or the partial pressure that you can calculate using Dalton's model. So just be aware of that. It's not the mixture pressure, it's the component or the partial pressure. I can also get things in terms of the number of moles and S bar. So you'll notice that I've got a bar over a lot of those terms. That R value, that's R bar, that's the universal gas constant. Those S bar not values or S not bar values, I don't know what you want to call it, those are tabulated for those 5 gases in A23. So you got it for CO2, CO, H2O, nitrogen, and oxygen. And your units are still kilojoules per Kelvin. You can also calculate delta little s. So you see that I'm multiplying by the mass fraction as opposed to the mass. Still getting kilojoules per kilogram of the mixture times Kelvin. And I also have an equation for that uses the mole fraction. Still a little bit ugly. You're dividing through by the molar mass, but you still get the same units. Kilojoules per kilogram of the mixture, Kelvin. All right, so taking those 2 bottom equations, once again, let's look at what we do if we assume that specific heats are constant. So if you make the assumption that specific heats are constant, that first equation with the mass fraction, you can use the equation for entropy change for an ideal gas with constant specific heats. So you know from Thermo 1 that that's this equation right here, and I've made sure to put a little subscript I after every single one of those terms to remind myself that I am talking about the component. The only thing that I dropped it from is the temperature, and once again, that's because by Dalton's model, the temperature of the component and the mixture are equal to one another, so I just dropped it for cleanliness, I guess. All right, so that second equation, the one that's in terms of mole fractions, well, I can simplify that delta S in terms of CP, this guy over here, except now instead of having it in terms of CP and the specific gas constant, I've got it in terms of CP bar and R bar. So once again, that CP bar, you can look that up, you can kind of calculate that if it's not given to you, and the R bar is the universal gas constant. Okay, so that's a lot of equations. That's exhausting. And how are you going to do it? Well, number 1, relax. You've got an equation sheet. You just need to know how to use it. You need to know what all of those terms are. So be comfortable with it. When you're solving problems, when you're going through and practicing problems, have that equation sheet out and make sure that you're using it. So it's very comfortable to use and you know everything that's on there. Number 2, keep track of whether or not you're talking about the component or the mixture. So if you're talking about the component, you make sure that there is a subscript I or subscript whatever component is on that term just to keep track, because if you don't have a subscript, that indicates that you're talking about the mixture, unless you put a little M there to indicate that you're talking about a mixture, however you want to handle it. And number 3, write down your units. Be really, really meticulous. Most errors that I see are they're unit errors where people are confused about whether they're talking about the component or the mixture. They don't know if they're multiplying by mass or the mass fraction. Write down your units and you'll find those errors more easily. So, all right. Well, thank you very much for watching. We'll work some problems the next time we meet.